All right, good morning, seventh grade. I figured this one would be easier to discuss over a video because there are a few things going on with Leanne, Gilberto, and Alana that we haven't seen yet. So I've already worked out most of the problems. Some of the problems that are not on here, I'm just going to talk about. So you'll check your answers just by by what I'm saying here. So, all right, so you've got 3 sponsor levels for Leanne, Gilberto, and Alana. So Leanne has a situation where it does not matter how many kilometers she walks, her sponsors are giving her $10 each, regardless of how far she walks. So if she gets injured or something happens, even if she walks no kilometers, even if she's at 0 kilometers, she's still making $10. Gilberto is very similar to what we've been, the graphs that we've been looking at in the past and the data tables. So he starts at 0, 0. So if he walks 0 kilometers, he doesn't get any money. But every time his kilometers increase by 1, he makes $2 per kilometer. So at 1 kilometer, he gets $2, 2 kilometers, $4, 3 kilometers, $6. So this Gilberto is very, very similar to what we've been working with in the past. Alana is a combination of Leanne and Gilberto. So Alana's sponsors are going to give her a flat fee or a flat rate of, no, not a flat rate, a flat amount of $5. So it's almost like she went to her sponsors and they all gave her $5. And then they also said, and on top of the $5, I'll give you 50 cents per kilometer. So this one, I think when I was looking through people's answers, this one I think had the most confusion. Leanne as well. Leanne and Alana had the most confusion, but Alana, when you guys were making the equations, you have to be very careful of the fact that she gets $5 first and then 50 cents per kilometer. So she starts at 0 with $5, and then you add on the first kilometer, 50 cents, the second kilometer, 50 cents, the third kilometer, 50 cents, but it's being added to that $5, okay? If you look at Leanne's, she's $10 all the way down. So that's indicated there. She gets that flat amount of $10, but it just stays $10 the whole entire time. A couple of things about the data tables, and I wrote it up here at the top. In this case, the independent variable, what goes on the x-axis is the kilometers, is the distance, and the money is dependent on that. So if you kind of think about, I know I've said in the past, just kind of say it out loud, is the money, how much you make depend on how far you walk, or does how far you walk depend on how much you make? And in this case, they're getting money based on how far they walk. So the money made depends on how far one of the students are walking. So just be careful of that. Your graph should look like this. So Gilberto again looks very similar to what we've graphed in the past. So he starts at 0, 0, and then he goes, over 1, up 2, over 1, up 2, or you can think of up 2, over 1, up 2, over 1. You can see the stair step happening there. Alana has stair steps too, but if we were in class, I would ask you, what's going on with Alana? What's different about Alana's graph comparatively to Gilberto's? And that would be, you'll notice she starts at 0 kilometers. She already has $5. So no matter what happens, she will make $5 no matter what. And then from there, every time she increases 1 kilometer, it goes up 50 cents. So 50 cents, 1 kilometer, 50 cents, 1 kilometer, 50 cents, 1 kilometer. So she has a stair step, but you can tell it's a little, it's less steep than Gilberto's graph. I didn't write Leanne's name here, but this is Leanne. And Leanne's graph, also something we haven't seen before. Like I said, Alana is kind of a combo of Gilberto and Leanne. We've got the flat amount, and then we've got a increase over the amount of kilometers. Leanne, you'll notice she is just maintaining on the graph visually at 0 kilometers, she's making $10, but that never changes. She's got a horizontal line going all the way across because it does not matter how many kilometers she walks, she gets $10 no matter what. So let's take a look at those equations, because the equations, Leanne's equation and again Alana's equation are just a little different than what you've seen before. And I did take a peek at your assignment that you turned in to me. So this is what I was kind of looking for. You had to do the data table, you had to do the graph, and then you had to answer number 4 for B. So Leanne's equation, so for all of these, you should be thinking about the 2 variables. The 2 variables always come from whatever's on the x-axis and what's on the y-axis. So you should be thinking to yourself, okay, what letter am I going to use to represent the money? And what letter am I going to use to represent the kilometers or the distance? So I chose M to represent the money and D to represent the distance. You may have chosen a different variable, but basically in all of these equations, you should not have more than 2 variables, and you have to have numbers in there because you can't, the goal is to use the equation to plug in and solve for either kilometers or money. So for example, if we focus in on Gilberto's equation, which I think most people got correct because it's very, very similar to what we've been doing, we have the money is equal to $2 times the kilometers times the distance, the kilometers that he walks. So if you think about this, if I know how much money he made, I can plug in, let's say he made $15, or let's say he made $16, since he's making it per kilometer. I could plug in 16 to M, and then I can solve for D like a river problem. So 15 or 16 equals 2D. I can divide by 2 on both sides, and I know that he would have walked 8 kilometers. Leanne, again, if we were in class, I would ask you guys, what is going on with Leanne? What happened to her D? She's got money here, but she doesn't have a D or a D variable that's there. So, and I'll explain here. So if you think about Leanne, how much money is she making per kilometer? So per kilometer, Leanne is making $0. So it's almost like, if you put M is equal to 0 times the D, so if I did M is equal to 0 D, you would have that no matter how many kilometers she walks, she gets $0. But we also know that she makes $10 no matter what. So once we have that 0D, we don't need to show 0D because 0D is just 0. So what ends up happening is no matter how many kilometers she walks, it's just $10. So all we need to know is that the money is equal to $10. M is equal to $10. That's all that it should have. Leanne's is the only one that has just one variable, because that D variable would essentially disappear once you did the 0 times D. So Alana, maybe I should have done Alana's first because it makes a little more sense talking about Leanne's. But you had a couple of options there. So if you thought about it, you could We know that she's making 50 cents, right? So if I go up to the data table, I see that it's plus 0.50, plus 0.50, plus 0.50, and that's happening for every kilometer that she walks, right? So I'm adding 50 cents every single time. But if I just had an equation like Gilberto's and it just said the money is equal to 0.5D, then what would happen here is when I plug in, 2 kilometers, I'm only going to get $1. And this is a great way to check your equations too. A lot of the equations for Alana were a bit off. Leanne for that matter as well. So go back to your equations and check them out. Plug in the kilometers. See, do a point tester, right? So here, if I took 4 and I plugged it into D, 0.5 times 4, my money would only come out to $2. But I know in my data table that she has made $7. So what do I need to do to change that? So these are the first equations that we're seeing where we actually have what looks like a constant of proportionality. Gilberto has a constant of proportionality with his 2D, but Alana is not, you have your constant rate of change, but you have to add to that. So if you think about it, she's got her constant rate of change, but every time she walks the kilometers, you have to add $5 to that amount. Because she makes $5 in the beginning. Some of you may have done it like this, and I actually did see a few of you did have the correct equation. And so if you think about it, all right, she makes $5, and then I'm going to add 50 cents per kilometer, 50 cents per the distance she travels. And you can, again, test this as well. So if I plugged in, any of these kind of coordinate pairs. So 6, let's say my kilometers are 6, I could plug 6 into D and I would get 0.5 times 6, which would be 3. If I add 5 to that, I would get 8 for my dollars. And when I look up here, I can check it and see that it's 8. So for number A4, I don't have it written here. I don't think I wrote it on the other page. I'm just going to talk through it really quick. So what pattern of change between the two variables do you observe in the table? So if you look, they want to know for each plan. So what's going on in the data table, what's happening in the graph, what's happening in the equation. I think I explained a little bit here of this, but I'll go through it really quickly. So Leanne, you'll notice that the pattern of change between the two variables here, this is just constant, right? So we see the 10, 10, 10, 10, and with Leanne's graph, you can tell that the pattern appears as just a straight line moving across. So between the graph and the table, the constant is 10. The constant is 10, and in the in the equation, it's just the money is 10, right? So we see it here, we see it here, we see it here. You can also see that the change is, the change of money is really 0. It's increasing by 0 amount each time. It's just maintaining that 10. For Gilberto, the pattern of change between the two variables, we can see that, between the money and the kilometers are multiplied by 2, right? Multiply by 2, multiply by 2, multiply by 2. Multiply by 2. We can also see kind of coming down here, we have a pattern of start at 0, add 2, add 2, add 2, add 2, add 2, every time the kilometers are going up by 1. You see that in the graph because that pattern, again, every time my kilometers increase by 1, my dollars increase by 2. So you can see that stair-step pattern. And then with Alana, we've kind of written already, I've written already the increase. So we start at 5, the pattern of change. So basically what's happening is I'm taking that $5 and here I'm adding the 50 cents, right? So 1 times 0.50. $5, 2 plus 2 times 0.50. $5 plus 3 times 0.50. And that shows itself here. We have a start at $5 and then we go, every kilometer, 50 cents. Every kilometer, 50 cents. Every kilometer, 50 cents. Every kilometer, 50 cents. And then that pattern of change shows itself down here as well. So start with $5. No matter which one you wrote, start with $5 and then take that 50 cents and multiply it. For all of these, you can tell, then this comes up in every investigation. So it's extremely important that you kind of see how these patterns, like what is happening in a data table. You can look at a data table and immediately tell whether it's linear or not. And that is because of the constant rate of change. If I am going up by 1 in the x-axis, or I could be going up by 2 or 3, but in these scenarios, I'm going up by 1. Then what happens here is if I constantly have the same thing, right? So my ratio between from money to kilometers, I've got a 2-to-1 ratio, 2-to-1 ratio, 2-to-1 ratio, 2-to-1 ratio, 2-to-1 ratio, and so on. Here, I might start at $5, but I have a ratio as I move up of 50 cents to 1, 50 cents to 1, 50 cents to 1. This constant rate of change tells me that it's a linear relationship. It tells me that, oops, that should be 1. It tells me that, every time, if I see this, I should be thinking to myself, all right, it's like a stair step. When I go to my graph, I'm going to have the up and over, up and over, up and over. For Leanne, now she still has a constant rate of change. Her change just happens to be 0. So you can have, her ratio from money to kilometers. She's 0 to 1, 0 to 1, 0 to 1, 0 to 1. For every $0, she's gone 1 kilometer. But then we'd have to add that 10 in at the end. So that kind of takes care of A4. All right, last ones. And then if you need to take a snapshot, I'm pretty sure I answered most of the questions here. I'm just going to talk a little more in depth. Well, I do need to talk a little more in depth about them. Okay, so for B, suppose each student walks 8 kilometers in the walkathon. How much money does each sponsor donate? How can you find your answer? So I'm just going to kind of look at 3 ways that you can find your answer. Because for both B1 and B2, B1 has you looking at, a constant of 8 kilometers. And then B2 has you looking at like, okay, you don't know the kilometers, but you know the money. So let's talk about both of those. So there's 3 different possibilities here. So if we know that the student walked 8 kilometers, you could have done one of 3 things. You may have talked about how you extended the data table. So if I extend the data table to go 7, 8, 7, 8, 7, 8, I can follow the pattern and get my answer. If I used the graph, so the graph might be a little bit harder because sometimes in graphs, we know what the patterns are here, but sometimes it's a little harder in graphs to get the exact numbers. But here it wouldn't be too hard. So if you had a data to my graph, I don't have enough room to extend it, but let's say I take Gilberto and I just keep bringing the line up. I could go to 8 kilometers and then follow my finger up to where the line hits. Same with Alana and same with Leanne. Leanne is the easiest one here. It does not matter how many kilometers she walks. She's just always getting $10. So that does not matter. So you could extend the graphs. The third thing you can do is use the equations. So I did it for Alana down here. Yeah, Alana's a good one to use since her equation is a little more complex than the other ones. But if I have 8 kilometers, I solve it kind of like a river problem, but I don't actually have to start balancing the equation. 0.5 times the distance. I know my distance is 8, so I plug in 8 to D, and I'm left with 0.5 times 8 plus 5. So I know that my money is going to be equal to 4 plus 5. So my money will be equal to $9. So 3 different ways to do that. Same thing with B2. So if I know that each student gets $10 from a sponsor, with Leanne, there is no way to know for sure because she always makes $10. So we have no idea how many kilometers she walks. We would need more information. With Gilberto and Alana, same thing here. You could keep, well, actually Gilberto you see immediately. So we know that at 5 kilometers, he makes $10. And then with Alana, you could just keep extending the data table until you get to $10. With the graph, you would go to 10, and then you would just look to see like, okay, Gilberto, I'm at $10. That's 5 kilometers. And then Alana's graph would have to be extended even more. So if you got a straight edge and you kept extending it, you would just go to where it's 10, and then you'd follow it down to see how many kilometers she walked. I solved Alana's again with the equation here, so you can take a peek at that. I solved it just like a river problem. I'll go ahead and put that river in there too, just so we can see it. So basically I plugged in 10 for the money, and then I just start balancing my equation. So I take care of any addition or subtraction first. I notice that my D is on the right side. Subtract 5 from both sides. That leaves me with 5 equals 0.5D. I'm going to divide by 0.5 on both sides. So my D is actually 10 kilometers. So it'll take Alana 10 kilometers to make $10. For B3, on the graph, does the point, what graph does 12, 11 lie on? Well, let's just start with what these mean. So my point 12, 11, 12 is always, this is always on the x-axis. So our points, and you should know this from past years and from past conversations in our class, but the first coordinate is always the x-axis. The second one is the y-axis. Kilometers refers to 12. 12 is the kilometers walked. 11 is the money raised. Without actually doing the work for this, I can narrow this down to Alana almost immediately, and I'll show you how. So we notice here, if I look, well, Leanne's out just because she'll never make $11. She just always makes $10. If you look at Gilberto, if you check and see kind of where $11 is, he makes $11 kind of between 5 and 6 kilometers, so he would be out. So the only one that really makes sense here would be Alana. If I extended Alana's graph, we should find that when she gets to 12 kilometers, she makes about $11. All right, and then the very last one, I'm going to highlight a couple of things here just so that you can see. So in Alana's plan, how is the fixed donation represented in the data table? So I've already circled it up here. Her fixed donation, the fixed amount is always when the X variable, in this case it's kilometers, the X variable is 0. Whenever you see 0 and a flat amount and then it starts increasing after that, your equation will always look like this. This amount, so I guess I'm going to the equation right now. So this fixed amount of $5 is always, whatever this amount is, it's always added to whatever the constant rate of change is. And then in the graph, you see it here. So whenever it's 0, your graph starts at anything other than 0. So that added money, that money that's constantly there before you start having an increase, it's always at 0 something. It's not 0, 0. It's 0, 5. So you add that to your constant rate of change. And then you'll always see that my graph starts at 5, not at 0. All right, I hope that clears at least a few things up. I know there was some confusion about Leanne and Alana. Some of you had reached out to me. I realize this video is a little bit longer than some of the other ones, but this is probably the most important investigation. It's the first investigation where we actually see something different than just starting at 0, 0 and having a constant rate of change. So, you know, you're going to work on 1.4 today, between today and tomorrow, and that has something that's just a tiny bit different. So you'll see kind of what's happening with that. But if you have any questions, reach out to me and let me know. Have an awesome day, you guys. I will see you later.